Good day to you all students. So we are going to learn part 6 of chapter 15 waves today. So today we are going to study about harmonics in waves. So what are harmonics? Harmonic series are the ratio of frequencies produced by a vibrating string or air column. So the first case we can consider of a stretched string which has a length L and is fixed at both ends. So as you see in the diagram below, when a string is fixed at both ends, a wave will travel from the first end to the second end and it will get reflected and return, forming stationary waves. So what you see here, this closed loop is a segment of a stationary wave, and the length of this segment corresponds to half wavelength, or L equal to lambda by 2. So if there are n segments, then the length will correspond to n times lambda by 2. So the first end we will consider as x equal to 0, and the right side end we will consider as x equal to L. Accordingly, we can formulate the different wavelengths and different frequencies. So as you can see, n equal to 1, then L equal to 1 into lambda by 2 or lambda by 2, and therefore lambda equal to 2L. Frequency is given by the formula V by lambda, therefore it becomes V by 2L. Now this is the lowest frequency the string can have, and therefore it is called the fundamental or first harmonic. The next one is at n equal to 2. As you see in the diagram at the extreme end, there are two segments. So here L equal to 2 times lambda by 2, or lambda equal to 2L by 2, and we are not supposed to cancel that. Frequency nu equal to 2 times V by 2L. So this is called the second harmonic. As you can see, it is a multiple of the first harmonic. So the first harmonic is nu V by 2L, and the second one is 2 times V by 2L. And so on, you get 3V by 2L, 4V by 2L, 5V by 2L, 6V by 2L for the frequencies. Whenever n equal to 3, n equal to 4, when n equal to 5, n equal to 6, and so on. So the harmonic series that we get is in the ratio 1 is to 2 is to 3 is to 4 is to 5 is to 6, and so on. So in a stretched string which is fixed at both ends, the harmonic series will be as seen here. Now look at this case where we get only odd harmonics. Now if you have air column in a pipe which is closed at one end and open at the other end, obviously the closed end will have a node and the open end will have an antinode. So the closed end we will consider as x equal to 0, and the open end will be L. Now L will be given as n plus half lambda by 2 in terms of the segment that is produced there, where n equal to 0, 1, 2, 3, etc. So in that case, you can derive lambda equal to 2 times L by n plus half. And frequency will be nu equal to n plus half V by 2L, where n is equal to 0, 1, 2, 3, etc. And in this case, we get the harmonic series only as odd multiples of the fundamental mode or odd multiples of the first harmonic. So it will be 1 is to 3 is to 5 is to 7 is to 9 is to 11, as we see in the next table. Now we have the same formula written here, and the diagrams show pipes or air columns which is closed at the first end and open at the other end. Now at the closed end we see there is a node, and at the open end will always be antinodes. So we have the length of the pipe will correspond to n plus half lambda by 2. So n starts from 0 here. So when n is equal to 0, L equal to lambda by 4, or lambda is equal to 4L, and frequency is V by lambda, which is V by 4L. So that will be the fundamental of first harmonic. N equal to 1, we have L equal to 3 times lambda by 4. Therefore, lambda is equal to 4L by 3, and frequency nu equal to 3 times V by 4L. So the second harmonic is missing here. After the first harmonic, we get only the third harmonic. Then when n equal to 2, lambda equal to 4L by 5, and frequency nu equal to 5 times V by 4L, or that becomes the fifth harmonic. So here in this case, we get odd multiples of the first harmonic as a harmonic series. That is why we have the ratio 1:3:5:7:9:11. Now the third case, we have an open pipe. Both ends are open. So at both ends we have antinodes, and only at the center we have a node. So the formula corresponds to L equal to lambda by 2, because the length of the pipe you have on the left side a lambda by 4, and on the right side a lambda by 4. So both add together, the length is lambda by 2, or lambda equal to 2L, or frequency nu equal to V by lambda, which is equal to V by 2L. Second harmonic also we have L equal to lambda, or nu equal to V by L, and if you write it as multiply the numerator and denominator with 2, you can write it as 2 into V by 2L to show that this is a second harmonic of the first one, a second multiple of first harmonic. So the second harmonic is also produced here. Similarly, third and fourth are also produced in an open pipe which has both ends open, and therefore the harmonic series will be 1:2:3:4, and so on. So we have discussed three cases here. The first was both ends fixed, where we get all the harmonics. Second, one end closed, one end open, you get only odd harmonics. And the third case, when both ends are open and the air column vibrates, you get again all harmonic series, all the frequencies. Next, we are going to study about beats. What are beats? When two harmonic sound waves of nearly equal frequencies are heard at the same time, we can hear distinct waxing and waning of intensity of sound with a frequency equal to the difference in frequencies of the two waves. This waxing and waning of sound waves are called beats. The beat frequency will be equal to the difference in frequencies of the two harmonic sound waves. Now this beats is a specialty of sound waves. When two sound waves of nearly equal frequencies, the frequencies, if they are equal, then we cannot hear beats. There should only be a very slight difference between the frequencies of the two sound waves. Only then we can hear distinct waxing. That means a rise to a maximum and a rise and a low, it goes low to a minimum. Waxing and waning of intensity of sound can be heard. And this waxing and waning keeps repeating at regular intervals with a frequency equal to the difference in frequencies of the two waves. So such sound intensity variations are called beats. So here the first harmonic wave, sound wave, is shown in the first graph, and let its displacement equation be S1 equal to A cos omega 1 t. And the second wave slightly differs in frequency, which is S2 equal to A cos omega t, 2 into t. So in the third graph you see the beats. Now this here, it is an example of two waves which are slightly different in frequencies, and S equal to, the resultant wave is given by S equal to S1 plus S2, which is A cos omega 1 t plus A cos omega 2 t. Now to add this cos A plus cos B, we have to use the trigonometric identity. So here we have capital A equal to omega 1 t and capital B equal to omega 2 t. So we have cos A plus cos B equal to 2 cos A plus B by 2 cos A minus B by 2. And you get this result as shown here. Now let omega 1 plus omega 2 by 2 be equal to omega A. And let omega 1 minus omega 2 by 2 be omega B. Now the amplitude of the wave is given as 2A cos omega B. So amplitude of the resultant wave will be maximum when cos omega B takes its limit from plus 1 to minus 1. Cos omega B, the maximum value it takes is cos 0 equal to plus 1. Then cos 180 equal to minus 1. So maximum value will take limits from plus 1 to minus 1. Then the amplitude becomes 2 into small a, which is the maximum. So the intensity of the resultant wave waxes and wanes with the frequency which is 2 omega b. So it will be 2 into omega 1 minus omega 2 by 2, which is omega 1 minus omega 2. But omega 1 is 2 pi into nu 1 and omega 2 is equal to 2 pi into nu 2. So omega 1 minus omega 2 will be 2 pi into nu 1 minus nu 2. Difference in frequencies of the two waves, and that is called the beat frequency. 2 pi into nu beat. So the beat frequency nu beat will be equal to nu 1 minus nu 2. So thank you students. That is part 6, chapter 15.